welcome to the weekend video on speeds of gases, or what determines how fast gases move, and also like what factors affect their speed. Okay, so one thing that we have to get straight, which I don't think I did a good job the first time we did this lesson, which was before the first test, which is another reason why I probably didn't go that well, is we need to understand that if gases have the same temperature, they have the same kinetic energy, and actually it probably should say average kinetic energy there. Okay, so a lot of times on the AP exam, I've seen questions when I've been looking through it where they'll give a table of gases with like lots of information about them, their temperature, their pressure, and they'll ask which gases have the same average kinetic energy. Okay, and it's always true, okay, that the gases with the same temperature have the same average kinetic energy. Okay, now, so here we see I have an example. So a gas of N2 at 300 Kelvin would have the same kinetic energy as a gas of oxygen at 300 Kelvin as well. And again, that probably should say average. Now, there's a common misconception that we need to get rid of, okay, that atoms at the same temperature are moving at the exact same speed. And that's not true. Okay. Now, we need to talk about what factors affect the speed that they move at. Okay. So here's the formula up here for kinetic energy. And kinetic energy is equal to 1/2 the mass of the particles times the velocity of the particles, or the speed of the particles squared. Okay. So from this formula, what we can learn is that if two gases are at the same temperature, right, they have the same kinetic energy. Okay. But the lighter gas, okay, has to be moving at a faster speed. Let's look at an example in order to understand that. So let's say we have two gases, and they're at the same temperature. It doesn't matter. Let's say they're at 300 Kelvin. Okay, and we'll just say that their kinetic energy, just to have a number, is both 100. Remember, they're at the same temperature, right? So they have to have the same kinetic energy. And we'll have gases gas A, and gas B, and say the molar mass of gas A is 10, and the grams per mole, and the molar mass of gas B is 5. All right. Well, we know for gas A, kinetic energy, okay, equals 1/2 mv squared, right? And we know the kinetic energy is 100, all right? And we have 100 is the, so we have the kinetic energy being 100 and the mass is 10, and we need to solve for v squared. So if we do this, we have 100, that's 5v squared, we divide both sides by 5, 100 divided by 5, which I probably could do in my head, but I don't feel like it, 20. And then v squared, we take the square root of both sides, and the square root of 20, I'm going to round. So the velocity here is 4.5 about. And then we'll do the same thing here. So again, kinetic energy is 1/2 mv squared. And the mass is 5 in this case. V squared is 100. This is 2.5 v squared. I'm going to divide both sides by 2.5. Get 40. And then we square root it. The square root of 40 is 6.3. Okay? I'm square rooting both sides. Alright, now, notice, okay, that this is a lighter gas. Its molar mass is lighter, and its speed is faster. Okay. Now, do you need to be able to do that math? Absolutely not. Okay, in fact, I'm going to erase this now, because you're going to see what you need to remember in a second. Okay, so what you need to remember, okay, is, okay, that gases that have low molar masses move faster than gases that have higher molar masses. So the speed of movement, okay, is based on the molar mass of the gas. The higher the molar mass, okay, the slower the gas will be, okay? Assuming that the temperatures are the same. Remember, we have to get the difference between average kinetic energy and speed. To summarize one more time, because this is so important, okay? At the same speed, okay, so at the same temperature, okay, two gases have the same average kinetic energy. However, the one that is lighter, okay, will be moving faster. Okay, so here's an example of a question. Compare the speed of helium compared to carbon dioxide if they are stored at the same temperature. So if we look at the molar mass of helium, if you look at your periodic table, is around 4. And I hope you memorize the molar mass of carbon dioxide is 44.0. So since helium is lighter, and they're at the same temperature, the helium gas particles will be moving faster, okay? But you have to remember they have the same average kinetic energy. Okay, so here's another question. So select the gas that will have an average speed closest to Ne. All gases are at the same temp and pressure. So Ne, again, it's molar mass that affects speed. So Ne has a molar mass, if I'm looking at the periodic table, close to 20. Okay. Hydrogen is close to 2. I want to stop writing. Stop writing. Boo. So my computer froze in the middle of doing this. So I'm going to start again on this slide, so I apologize. So we were asking which one, at the same temperature and pressure, which one of these gases is going to have the closest speed to neon. And I wrote down next to all the elements the molar masses. Okay? And remember, speed is related to the molar mass. The lighter the molar mass, the faster the molecule will go at the same temperature. So the one that has a molar mass closest to neon is water. So neon and water at the same temperature and pressure will have the closest speed. Okay, now, these are just some definitions. So effusion is if you have a gas in a container, and there's as I was interrupted by Mr. Mays. So effusion is when you put particles of gas in a container, and there's a tiny hole, and they leave through that tiny hole. So that process is called effusion. And then we also have diffusion, which is when you have a gas in a space and it spreads to fill the space. So not that you need to really know these words, but they may appear on the exam. They really just mean that the gases are moving. Right? Either they're moving through a hole, or they're spreading through a space, depending upon if you're talking about effusion or diffusion. Now, so in the old exam, you used to have to learn this equation here. Okay? We do not need to learn this equation or use this equation, so you'll probably be happy. But there was a law called Graham's law of effusion, which says that you have two gases, okay? The speed at which they effuse through the hole is going to be inversely proportional to the square roots of their masses, okay? All that really means, and all you need to know, okay, is that the lighter the gas, okay, the faster it's going to move through the hole. So here we have two containers of equal size, and we have helium gas, okay, which is much lighter than ethylene oxide. Okay, and they're in this box and we're allowing the same amount of time. So let's say 10 seconds has passed here and 10 seconds has passed here. You'll see within those 10 seconds, many more helium particles were able to effuse through the hole than ethylene oxide particles were able to effuse. Here we have, I don't want to count, but more than 10, and here we have only 3. Now the reason that is because helium is lighter, okay, than ethylene oxide, and therefore it travels faster. Okay, so the lighter gas will effuse faster. Than a heavier gas. And again, this math we do not need to know how to do. Alright, now we're up to the part of the lesson that caused problems on the first day of the gas lesson the day before the test. So I need to explain this much, much better. This is the Boltzman Distribution Curve. And what it shows, okay, is we have two gases at two different temperatures. What's important to realize is the number of particles in each sample is the same. Okay. And it shows you the number of particles. We have number of particles on this axis and speed on this axis. And what this graph shows you, okay, is the number of particles moving at each speed. Okay, so if we first take a look at the gas that's at 80 Kelvin, okay, that's the lower temperature, and we compare it to the gas at 300 Kelvin, which is obviously the higher temperature, there are two things that are different about this gas, about this graph. Okay, when the temperature gets hotter, okay, this graph, which relates speed to the number of particles, shifts to the right, okay, and becomes flatter. Okay, so a lot of times the AP exam will ask you to identify temperatures of a gas using on these graphs. The one that is more spread out or more to the right is the hotter one. And there are two things you need to know. The graph of the hotter gas has more spread. Okay, which means there are more possible speeds. Okay. What's also true in the hotter gas is the average speed is hotter. I'm sorry, the average speed is faster. Okay? And the average speed is where the hump is. So if we look at the gas that's at 80 Kelvin, its average speed is about 200 meters per second. So that's the highest, that's the highest where most of the gas particles are. For the gas that's hotter, its average speed is about 400, okay, meters per second. Okay? So when you increase the temperature of a gas, okay, the average speed increases. And again, the average speed on this graph, okay, is where the hump is. Now, the other thing that you need to notice, okay, which is not as important, okay, but, okay, at the average speed in particles that are moving faster or are at faster temperatures, okay, there are less particles at that high average speed. This hump here, okay, is higher than that hump here. So let's summarize. Okay, when a gas is at a high temperature, these graphs shift to the right. And the two things you really need to know is that gases at higher temperatures have a greater spread. There's more possible speeds. Okay, and their average speed is higher. Right? This graph has its hump is at a higher temperature than this graph. Okay. Now there's a typo in this because I'm an idiot. So we don't know. I changed the graph and didn't change the text. So ignore this. Okay. There's one more thing that we need to learn. Okay. And this graph, while this graph here, okay, showed the same gas at different temperatures. Okay. So this was I probably should have started with that. This graph was the same gas. So maybe it was like oxygen gas at 80 Kelvin and oxygen gas at 300 Kelvin. Okay. This graph shows two different gases, okay, at the same temperature. Okay. And the question that they ask is they want to know which line is HE. Okay. Now remember, gases that are lighter move faster. Okay. So HE has a molar mass of about 4 and NE has a molar mass of about 20. Okay, so the molecules of HE are going to be moving faster, or have faster average speed. Remember, their kinetic energy is the same, okay, but the HE molecules have faster speed. Well, which one shows, or which graph shows, where more of the molecules are moving at a faster speed? Well, that's graph B, right? Graph B, the average speed is faster because it's more on the x-axis. So the graph here, this is HE. And the graph here is NE. Again, what's the sort of main idea? If gases are light, okay, and they're at the same temperature, they're going to have a faster average speed. So their graphs are going to be lighter gases, graphs are going to be shift more to the right. Okay, that is it. Have a good weekend.